All right, everybody, let's get started on 14.3. Do this. 14.3. We're still on day 24. This is the same day. If you're watching this separate video, same day. We're doing 14.3, and this is on graphing polynomials. All right, so it's important to note that polynomials they are continuous and smooth. This means no breaks in the line. What are you yelling about?
It's a stupid joke I heard once.
Is it derivative related?
No, totally related nonsense.
I'm sure it's about the curves on a woman.
No,
No.
it's not.
There's a lot of math jokes that quickly turn into
Yeah,
smooth and curvy.
Get a little out of hand. Yeah.
Smooth means no corners. Like absolute value has a corner, no cusps kind of thing. And it's good to know that an nth degree polynomial has at most, this is very, very important, at most, n-1 turning points. A turning point is where the graph goes from increasing to decreasing. Kind of like that, or decreasing to increasing. Like that. Do you even know the joke? Because you're still smiling about it.
No,
It's just a partial joke in his head. He's fucking loving.
not what it is. It's not even a joke, it's just a reference, like a video.
Are you sharing it? Is it not sharing it because it's inappropriate?
It's a video, I can't say it, it wouldn't make sense.
How's that a good fucking joke?
Say it.
I'm gonna believe this. So when I say at most, f of x equals x cubed does some shit like this. It's increasing the whole way. But if I have like, I don't know, x minus 1, x minus 3, x minus 5, this will be an x cubed plus some other shit here, plus some stuff. This is going to go through 1, 3, and 5. It's going to do some shit like that. So it turns here and it turns there. Those are called the turning points. And notice there's only two, which is 3 minus 1 or n minus 1. So finding turning points.
Turning points are kind of like vertices.
On a parabola, it is a vertices.
Yeah.
It's the vertex on a parabola. That's a great comment. Vertex on a parabola. And parabolas only have one when it's x squared, so it's 2 minus 1. So finding turning points, this is an early calculus topic. I'm pretty sure it's in chapter 1. When you start doing calculus, they're easy to find. But we're not going to do it. When I give you some examples today, I'll give you the turning points. I don't know if Alex is going to give you the turning points or not. But if it doesn't, I'll show you how to wing it. Because let's face it, if you don't know, you got to wing it. Or like get out a computer, but sometimes all you really care about is a quick sketch. We just did some equations. Which ones did we do that looked good here? Which one had all positive root or all roots? That one did. I'll come back to doing that one in a second. Okay, so the things we want to plot when we're graphing these. Is everyone done with that? No, maybe it's still writing. Okay, he's still writing. Davis is indecisive. Everybody's still writing. I was rushing. Slow your shit down, Jonas. All excited. This section is not too bad. It's pretty straightforward.
Parabola, or knowing these turning points, like that problem, right? Is both of the turning points would be like jet lines, or like
Yes,
is-
horizontal tangent lines.
yeah.
Horizontal tangent lines have a slope of 0, and that's really easy to find slope of 0 in calculus. You're doing the same thing as finding the roots of the derivative. It's really easy. This is really like finding turning points in calculus. Once you understand how derivatives work, which is chapter 1, fucking easy. Polynomial derivatives are the easiest of the derivatives. Like it's the when you start doing derivatives, the first one you learn because polynomials are the easiest. So you can like the first time you learn derivatives, you can all of a sudden immediately graph these fucking things, which is cool. So I wanted to show you something real quick. This is in the textbook. For the function y equals 4x to the 4th plus 5x cubed minus 1, I can immediately eliminate all of these as graphs without plotting a single fucking point by looking at them. X to the 4th should have 3 turning points at most. This one goes down then up. That's 1, 2, 3, 4. So this has got to be 5th degree or higher. This one has a gap. It's got to break in the line. So it's not continuous. It can't be a polynomial. And this one's got a little corner. It's got a cusp. And polynomials don't have cusps. Polynomials are just like nice rolling hills. So all of those can be eliminated immediately. Go, nope, that's not it. That's a lot of shit to sketch out though. So I'm like, let's just show you that. All right. So how do we graph these? Couple things we're going to do. Always good idea to plot any intercepts. Y-intercepts and x-intercepts. This one's easy. On a polynomial, it's a sub 0. Every other term has an x in it. So when you plug in x equals 0, the y-intercept is, like if I've got f of x equals a sub n x to the n minus 1, or x to the n plus a sub n minus 1 x to the n minus 1. The y-intercept happens when x equals 0. And I can see if I plug in 0 for x, it wipes out every term but the last one. Finding this, it's all about finding the roots. So this is what we did in 14.2.
And if we had imaginary numbers, that would mean, if we had imaginary roots or.
They don't cross the x-axis.
Means that
So like that last one we had, where we had plus or minus 1 twice. We'll sketch it on decimals. But we're gonna try to sketch it by hand first, but with what we know. Okay, so. Let me slow down. Megan's rapidly scribbling stuff down. She's like, fuck it, slow down, Jones. So to motivate the next idea, I'm going to show you the equation we're going to do first. The one we're going to do first was f of x. We just did this in the last section. X cubed minus 5x squared minus 9x plus 45. We saw that this factored into x minus 5, x plus 3, and x minus 3. I think I said those in the backward order. So x equals 5. Or plus or minus 3 are the x-intercepts. The y-intercept is 45. We're going to look at that in a second. So to motivate, like, this is telling me where it crosses the axis. I've got, I don't know, 45 is way up here. And 3 and 5 are probably like here and here. And negative 3 is there. So just looking at it, it looks like it's going to come up here. It's got to cross here. I don't know if it goes above it or if it goes above it afterwards, but eventually it crosses there, it comes back down here, it's got to cross here. And it looks like it goes like this. Just with the roots and the intercepts we have right now. Just being able to connect these 3 dots tells me this has got to be above. And I don't have any other roots over here, so I know it doesn't go back up. And I don't have any roots past here, so when I know it goes up, it doesn't come back down. So that's what I think it's going to look like based on just on the roots, but let's discuss some more stuff first. I'm going to factor out x cubed. If I take x cubed out of this one, it's 5 over x. If I take x cubed out of the 9x, I have 9 over x squared. And this would be 45 over x cubed. So like figuring out what end behavior is, what about, it's called end behavior, towards X equals negative infinity or goes towards negative infinity, or X goes towards positive infinity. That's what I mean by end behavior. At the ends of the line, at the ends of the graph, what are we looking at? So, yeah,
Or to take a guess where the graph is going positive infinity.
it's gonna go upwards towards positive infinity, it is, that's not what I have sketched here, but. Just looking at the equations, let's motivate this here. Ignoring the x cubed out front. What if I plug in infinity? In the parentheses for x. I have 1 minus 5 over infinity. Minus 9 over infinity squared, which doesn't even make a lot of sense. Over infinity cubed, which makes even less sense. These are all just infinities on bottom. What's 1 divided by 100? 1/100th or 0.01. It's a penny in terms of dollar. 1 divided by 10,000 is 0.0001. 1 divided by a million has 6 zeros before the 1. As x goes towards infinity, these all go towards 0. Which means the only one that's really impactful at infinity plus or minus infinity is the largest term, largest degree term. So what this boils down to, so f of x equals a sub n x to the n plus a sub n minus x to the n minus 1, all this good stuff we've been doing before that you're probably tired of seeing. As x goes to positive or minus infinity, f of x looks approximately like a sub n x to the n. So what does x squared look like? It goes like that to the left and like that to the right, right? They both go up. Actually, let's see this on the page. So if the first term is x squared plus some stuff, it should go up on the left and up on the right. And we know that. We already know how to sketch any quadratic. We've done this. X cubed does this. Like a sideways S, yeah. So anything with x cubed plus a bunch of stuff, it might be way on later, but it's going to do that. Kind of like what I drew right here. So there might be some shit going like that, or it might just be like that, but one of these is going to happen. It turns out x to the 4th, x to the 6th, just those, they all do shit like that. Just the bigger this number gets, the flatter it kind of like goes like more like this. This is like, this might be x to the 6th, this might be x to the 4th, and x squared's got very little of a, like anything near between -1 and 1 gets pretty flat because you're raising it to the 4th or 6th power. But they're all pointing up on each side. So if n is even,
Well, and
with x to the n,
if it's negative, then it's gonna.
yeah. If n is even, we have two options. If a sub n is greater than 0, they both point up. And if a sub n is less than 0, they both point down, like when we have a negative parabola. I thought I killed that pin, but here it is rearing its ugly head again. That was n is even. If you look at n is odd. It actually does something similar to x cubed the whole way. If a sub n is greater than 0, it's down on the left, up on the right. And if a sub n is less than 0, it's up on the left and down on the right.
And it also does that elbow thing. It's sharper.
Yeah, the larger the degree,
7.
like x to the, like so x cubed does this. X to the 5th gets a little more flatter in the region like that. It's between -1 and 1. We'll play with it on Desmos.
What would it look like if there were like, if it like ribbed out, like there were a bunch of, not just like that, but several up and down sections?
So generally, when we only have this, we only have the x to the high power term. When we have a bunch of sections, we have equations like this, where there's more terms that are lower. So that's what changes that. As long as there's another x term in there, it's going to change it. If there's just another constant, the constant just moves it up or down, but another x term shifts it. Except on quadraticals. That's always you just step with one. Okay, so we've got our intercepts. And we've got our end behavior. So that tells me with our f of x equals x cubed minus 5x squared minus 9x plus 45. And we saw that x equaled 5, 3 or -3. Let's say that's at 45. Oh, -3. Without knowing where the turning points are, I'm going to, this is how you would just sketch it with what you got. Plot the intercepts. So plot intercepts. Step 1. Step 2. Sketch end behavior. And it always looks like the largest degree. So x cubed here, and it's got a positive number in front, it's gonna look like that. So I'm gonna do some shit like this. So that's me sketching end behavior. Three, connect dots with turning points where you can. And I'm going to say right now, since this is for any ruling, no multiplicity. I don't want to show you multiplicity because there's no multiplicity on this one. But on the next, like one of the, we had plus or minus one show up twice in that one. So we had x minus 1 squared, it actually affects the graph. So we're gonna look at multiplicity in a second. So connecting the dots, I know down here, it's gotta do some stuff like that. And like 3 is in the mid, like this one, this intercept is like 3 away from here and 3 away from here. I think it might actually be the turning point, but I don't know. We'll sketch in a second. I'm going to treat it like it's the turning point. And I know it's got to cross here. And I know this is coming in like this. I don't know how far down it goes, but I know it's got to go down and find a way to connect the dots. Let me load up Desnants while you're drawing that, and I will put this bad boy in. That's all there is to this section, believe it or not, other than the multiplicity.
Sweet.
It's not really a hard section, not too bad. The hardest part is finding these roots.
And then that will complete, we have one more section and.
We're doing it on Thursday.
Oh, okay.
That is the rational functions, which means we have variables in the denominator, which means that's where we get asymptotes of shit. So how do we find the lines for the asymptotes and stuff like that? It's not a bad section. It's pretty interesting. So let's take a look at this graph on Desmos. Is everyone ready?
Yes.
You don't even have your pen in your hand. You better be ready. So we look at it. It looks like it crosses at. Oh, fuck. There we go. -3, 3, and 5. We got our intercept up here. It looks like the peak is a little to the left. So I was wrong. That's the turning point. Down here is the other turning point. So calculus will show you how to find where that is. Finding the y value is easy. You just plug in the x. It's finding where the x position is. That's the calculus step. And we can see it goes down on the left and up on the right. Right?
Yeah.
So how does multiplicity affect this?
Well, if you have 2 different points, then like the way that the graph, whether it's gonna be negative or positive.
So let me show you. I'm just. How many times, what exponent should I have on this one? Give me an exponent, somebody. 1.
X squared.
All right, we'll do a squared. Are we just gonna do straight up x squared or x plus something squared?
X squared plus 6 8 or yeah 7. X squared plus 1.
I don't want to do x squared plus 1 because that's complex. I'm just trying to show multiplicity right now. Let's do one where it's a little higher. Let's do x minus 7 cubed. All right, so what degree polynomial is this? Finding the degree of the polynomial is actually pretty easy. Degree of polynomial. Just look at the x's and their exponents. X to the first times x squared times x squared times x cubed. This is an x to the 8. There's no number in front of this, which means a sub n is, or a sub 8 is 1. It's even, which means n behavior is both upwards. Okay, so we've got our n behavior right here. Just look at the x terms and their exponents that go with them. You could be a psychopath and multiply this out. I'm not going to, because while I may be psychotic sometimes, I'm not a psychopath. Or I don't know. I don't know if that came out right. Maybe I am a psychopath, but I'm not psychotic. I don't know. Something's wrong with me. I know that. So multiplicities, what does this do on a graph? So let's say it's x minus a to the n. If n equals 1, like we've seen,
Well, then the weird question here is that this graph, like you were saying, almost certainly doesn't have all of those intercepts.
this graph definitely has all these intercepts.
But it's an x to the 8.
You haven't even let me finish. Look, let me get the goddamn lesson. We got 10 minutes left. All right. So it's either can cross upwards or it can cross going downwards, but it's crossing looking like a line. It kind of crosses straight up. If n equals even, this is my x-axis each time. If n equals even, the graph bounces off the graph bounces off the x-axis. Bing! Bing! In fact, depending on where I put the y-axis, this looks like y equals x squared, and this looks like y equals negative x squared. Is Bing not a... you like something there too much.
No,
All right, and it's odd. Greater than 1. What does x cubed look like going across the axis?
X to the cube.
Yeah, x cubed kind of does some shit like that. And negative x cubed kind of does some shit like that. So like the way I would describe this, and this is for any odd exponent that's greater than 1, kind of wiggles or shimmies across. It's not straight, doesn't bounce off, but it still crosses. Kind of does like a little sway, it's dancing across the line. However, whatever word you want to use to describe where it doesn't go straight, but it does some shit like this. You'll have better words for it when you get to calculus. It's called a concavity change, but I don't want to go into concavity here. So what are my roots on this?
it could be a 3, 2 negative 7s, 2 negative 1s, and 3 7s.
So this is I'm just gonna say M2 for multiplicity 2. And that's multiplicity of 3. Shit, that looks like a square. I don't want it to look like a square. I'm gonna say multiplicity there. So if I draw my graph. And the y-intercept is gonna be fucking ugly. The y-intercept is -3 times 7 squared times -7 cubed. I don't even wanna know what it is. But I can figure out if it's positive or negative by doing the rest of the graph. So let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm gonna plot my points there. I have -1 is here. -7 is there. 3 is here. And 7 is here. Agreed on that? End behavior tells me they both point up on the ends. So at -7, I know it bounces off. Kapow. At +7, I know it kind of shimmies across. Because it's an odd.
So,
And now I know it's got to cross here. So this must do some shit like that and do that. -1 is a bounce though. So it's bouncing off again. 3 crosses. So I know my y-intercept is positive, and it's probably way the fuck up here. Like really high up. And fuck. I feel like Desmos is fucking tripping out.
yeah, as I said, I think Desmond struggles with this kind of graph or something.
Desmos is really struggling.
I was trying to figure it out with this,
Like,
Yeah,
look at that, it's just fucking,
yeah.
it's got the -7. It's got the -1. Oh! I know what it's doing. We said it bounces there. If I scroll in enough,
Stop it, no way. Ah, look at that. Oh,
it just looks like it struggles.
what's that hell?
What the problem was is our eyes struggled. Our eyes couldn't see the difference zoomed out. Right? So it did bounce off. And I'm going to assume, let me get this out far enough.
So it's just that this is in fact a ridiculous graph. This is just.
Yeah, I picked random numbers and did something absolutely ridiculous. God damn, this is a lot of fucking scrolling. We see the bounce of -1. I'm not going to zoom in there again. I'm not going to go up to, looks like 7 to the 5th power times 3. But we can see it crosses at 3. And if we come over to 7, look at that. Does it cross directly over? No, it shimmies across. So, like, big picture, I wasn't able to find the turning points very well. Because let's face it, they're really large. I can't even go large enough to fucking see the top or the bottom of the graph. easily. But turning points, if they give it to you, they might, you just plot those as well, and that's where you know it curves. I'll go over an example on Thursday with turning points given to you. I kind of think it's self-explanatory. If you know where the turning point is, you just make that's where the fucking curve it turns. Cause here I was like guesstimating where it turns.
Well,
Here I was fucking wrong. It should have been way steeper, you know.
well, in the y-intercept, I guess this year, there would still be a y-intercept with all this.
Yeah,
And that y-intercept.
it should have been way up here.
Yeah, it's like 7 to the 5th times 3.
Right.
Yeah, so it's like, yeah, that's a.
So I knew my graph was wrong. But the overall behavior is correct. I had the ricochets or the bounces in the right spot. At x equals 1, it just crosses over. At x equals 7, it kind of shimmied over. End behavior was pointing up on both sides.
Would it look more normal if we changed the 7s to 2s? Because it would be much smaller.
How about I make one of them a 1 and one of them a 2? It's a little easier to see. So like x plus 2, so a -2, bounce. -1, bounce. 3 times 2 squared is 12. So it's crossing at 12. The turning point looks like it's a little to the left. At 1, it's a odd greater than 1, so it shimmies across. And at x equals 3, it's a 1, so it just crosses and is directly over. So if you have the turning points, like another, like they might give you a problem with tells you turning points are at -0.06 and 12.12. So you kind of like plot where those are. You're just adding more points to your graph, but you know that's where they're bouncing as well. It's 5 o'clock. I know I'm over the line. Oh, real quick, we did y equals x to the 4th. Minus 6x squared minus 27. Ah, fuck. Let me turn off the blue line. And even though it should have 4 roots, it's only crossing in 2 spots because 2 of them are complex. So it still has, we still see the 3 turning points here, 1 less than the 4. But like there's only 2 roots. So complex ones where you see complex numbers, you're still going to see graph, it just doesn't, there's no root, we're only finding roots there. And then we don't have a complex root doesn't show up. All right, let's call that a wrap.